Alright, so in this section we'll be looking at something called power series. A power series we can kind of think of as just an infinite degree polynomial. Right, so one example of a power series would be the sum from n equals 1 to infinity of, let's say, just x to the n. Right, so this would be x plus x squared plus x cubed plus x to the fourth, and so on. Right, now we can make this a little bit different by what we call centering the power series somewhere else. Right, so if instead I wanted to change all of these to say x minus 1, x minus 1 squared, x minus 1 cubed, and so on, then what I would do is I would just make this a right here equal to 1. And that a value, we either say that we're centering our power series at x equals a, or that this is a power series about a. Now let's say I wanted to, right, so then this should have been, if I want it to look like that, it would be x minus 1 to the n. Now let's say I want to change the coefficients of all of these. Then what I can do is, well, suppose I wanted all the coefficients to be 2. Then I could just write something that looks like, so let me do this again. Let's get rid of this. I could throw a 2 inside of here. And now this is going to be 2 times x minus 1, 2 times x minus 1 squared, 2 times x minus 1 cubed, and so on. Right? And so this c sub n, this is called the coefficients of our series. If I want my coefficients, if I don't want them to be the same number every time, right, we can kind of think of, well, this is going to be our a1 term, a2, a3, and so on. And so then I'll create another sequence, which is the c sub n sequence. So let's say I wanted the coefficients to be like 1, 2, 3, and so on. Then I would just make this c sub n sequence 1, 2, 3, and so on. So our c sub n is always just going to be the coefficient of x minus a to the n. Right, so we have some series, we'll write something where we have a x minus a to the n, and then everything that's being multiplied by that is going to be our c sub n. So suppose our power series converges for all x values that lie in this interval right here, and that it diverges for all other values of x. Then we say that I equals a comma b, this interval. We say that I is the interval of convergence. So the interval of convergence is just going to be this interval where our power series converges. The radius of convergence is going to be whatever the length of I is. So suppose we have I equals, let's say it's, I don't know, the interval from -2 to 2. Well, the length of this interval would be 4. So R is going to be equal to 0.5 times 4, which is equal to 2. Alright, so you can kind of think about this interval like if we put it on a number line. Right, if I'm going from -2 to 2, I have to travel a distance of 4. And so our radius is basically we take the center, and then we see how far is it from the center to one of these endpoints. And we can see that going to either endpoint, it's going to have the same distance. That's why we call it a radius. Right, you can think about it as if I drew like a circle right here. Then the radius is just the radius of this circle. Okay, so again, I is going to be our interval where our power series converges, and then R, our radius of convergence, is going to be half the length of that interval. Now, when you're given a power series, there's only 3 possibilities. One possibility is that this power series will only converge for one specific value of x. In this case, we say that the series only converges for x equals a. right? We know that because here we would have 0 to the n, so that's just 0, times our coefficient, so we have 0. So we're adding 0 infinitely many times, which means that the series is going to converge to 0. All right? So in this case, we would say that I, the interval of convergence, is just this one number, a. Okay? And so in this case, our interval of convergence, well, it has a length of 0, which means that our radius of convergence is going to be equal to 0. Another possibility is that the series will converge for any possible value of x, meaning that I can plug in any real number for x, and this series will converge. In this case, we would say that I is our interval of convergence is all real numbers, which means that our radius of convergence is going to be infinity. The third possibility is that there's some positive number r such that the series converges if the absolute value of x minus a is less than r. Right? So if it converges in this interval, then it's going to diverge everywhere else. Okay? In this case, we say that r is the radius of convergence, and the interval of convergence has to be at least negative r plus a to r plus a. The reason I'm saying at least here, and this is so important, is that this doesn't guarantee whether these endpoints converge. We would have to test the endpoints after this. Alright, so now let's start looking at some examples where in each example we're going to be trying to find the c sub n, which is the coefficients of the power series, the center of the series, right, so that's that a value, the radius of convergence, which is our big R, and the interval of convergence. So I'm going to give these some different colors. So our first thing, if we want to find c sub n, then we need to write this, this part right here. I need this to look something like c sub n times x minus a to the n. So that'll be my first goal. Well, here, so let's see, I'm going to call this part 1. So in part 1, we have 3 to the n x to the n over n squared plus 1. Well, that would be the same thing as 3 to the n over n squared plus 1 times x minus 0 to the n. And so here, we can see that c sub n is going to be this part right here. So c sub n is going to be 3 to the n over n squared plus 1. So if I asked you for the coefficient of, say, the sixth term, then what you would do is you would plug in 6 into the c sub n to get the coefficient, right? And so it would be whatever c sub 6 is. And if I asked you for the sixth term explicitly, then this would be c sub 6 times x minus 0 to the sixth, right? So just c sub 6 times x to the sixth. Right? Another way this could be asked is, in this series, what is the coefficient of x to the 8th? Well, that would tell us that we're trying to find c sub 8. Okay, now let's try to find the center of the series. So we'll call this part 2. Well, once we've done part 1 and we've gotten it written in this form, it's actually not too bad, because this is going to be our center. The reason I know that is because our power series is supposed to have the form x minus a to the n. Well, this one's going to be x minus 0 to the n. So that tells me that a equals 0 is the center. Now for part 3, the radius of convergence, now I'm trying to figure out, okay, where is this thing converging? So this is part 3, and we're going to label, let's see, this part right here, we'll label this as part 4. And it turns out that part 3 and part 4 are actually going to heavily rely on each other. So, in the past, if I had something like the series given, and generally in the past, instead of x to the n, we would be given some value for x. So something like 5 to the n or something like that. Well, in the past, when we were doing these types of things, whenever we had constants to the n, we were always using the ratio test. So let's try to apply that here. So when I'm using the ratio test here, the first thing I'm going to note is that all of these terms are positive, right? 3 to the n will always be positive because n goes from 0 to infinity. Now, x to the n, we can choose any value for x. So what I want to be careful about is what I just said, that everything's going to be positive. Well, the 3 to the n and the n squared plus 1 will always be positive. But if I chose, say, -2 for x, then this would be an alternating series. So I'm going to be careful and make sure that I throw in my absolute value signs along the way. The next thing I'm going to do is notice that this right here is actually just 3x to the n. So in my ratio test, we'll have 3x to the n plus 1 over n plus 1 squared plus 1 over 3x to the n over n squared plus 1. And then, of course, I'm going to throw in my absolute value signs like we should for the ratio test. Okay, well, this would be equal to the limit as n goes to infinity of, let's see, our 3x to the n plus 1 will cancel with a 3x to the n, so that'll leave us with a 3x on top. And then we should also be multiplying by n squared plus 1. And then on bottom, we'll have n plus 1 squared plus 1. Right, so here all I did was convert this fraction into one fraction and then cancel things out as much as I could. All right. Well, what I want to notice here is that 3x, this isn't a variable, this is going to be a constant, because we're going to choose some value for x. So let me note that real quick. This right here is some constant. Okay, well then I'm looking at our highest degree rule for n. So I'll have an n squared on top and an n squared on bottom, which tells me that, let's see, I need a different color. Let's use red, why not? This part right here, this is going to go to 1, right? As n goes to infinity, this will go to 1. Now, to show you the math that's happening here, we can look at this as limit as n goes to infinity of, let's see, we'd have absolute value of 3x times the limit as n goes to infinity of, now we'll have n squared plus 1 over n plus 1 squared plus 1. Alright, well, now we can see that this limit right here, if we use L'Hopital's rule or highest degree rule, this is going to go to 1. So what we're going to be left with is the limit as n goes to infinity of the absolute value of 3x. Now, remember, if we're looking for where this thing converges, the ratio test tells me that this is going to converge so long as this limit is strictly less than 1. Okay, so what I really want, that means that the absolute value of 3x has to be less than 1. Right, because there's no n's affecting this. So the limit as n goes to infinity of the absolute value of 3x is just the absolute value of 3x. Well, this means that negative 1 is less than 3x is less than 1, which means that negative 1/3 is less than x is less than 1/3. And so what this tells me is that r is going to be equal to 1/3. Now the next part, number 4, part 4, was for us to find the interval of convergence. So we know that I is at least, remember this should be negative r plus a. Well, let's go back. Our a was 0. So this is going to be negative 1/3 plus 0, which is negative 1/3. And then we should have r plus a, so 1/3 plus a, or 1/3 plus 0. So what we need to do is we need to check the endpoints. So what I'm saying is that we need to check, so let's see, check if x equals plus or minus 1/3 converges. To do this, you would take, so you could start with positive 1/3, and you would plug that back into our original series for x, right? So plug it in for this x. And then you would want to use one of our tests to see if it converges. Then you'll want to do the same thing for negative 1/3. This will be a good chance for you to practice our tests. So I'll tell you that x equals positive 1/3 converges by the comparison theorem, and x equals negative 1/3 will converge by the alternating series test. Since both of these converge, that means that I is going to be equal to negative 1/3 to 1/3. So that tells me that for this series, if you take any x value between negative 1/3 and 1/3, and you plug it into this series, then it's going to converge. That also tells me that if you take any x value that's not in that interval of convergence, and you plug it in, then this thing is going to diverge. Now let's look at example 2. For example 2, we're going to be doing the exact same thing as last time, just with a different series. So first I'll note that, let's see, c sub n, well, let's see, we have 2x minus 1 to the n over 4n minus 1. So this is the same thing as 2 times x minus 1/2 to the n. 2 times x minus 1/2 to the n. All I did was I just rewrote 2x minus 1 like this. Over, let me get rid of that, over 4n minus 1. Well, that's the same thing as 2 to the n times x minus 1/2 to the n over 4n minus 1. So c sub n will be equal to 2 to the n over 4n minus 1. Now, like I mentioned last time, once you've done this, it's relatively easy for us to find the center of the series, because now we just use this part right here. Okay, so we have x minus a to the n is supposed to be equal to x minus 1/2 to the n. So that tells me that a equals 1/2 is the center of our series. Alright, so now we'll proceed with the next step, which is to find the radius of convergence as well as the interval of convergence. So again here, when we plug in something for x, this top is going to become a constant to the nth power. And so this tells me that we're going to be using the ratio test. So we'll have, by the ratio test, limit as n goes to infinity of, let's see. So I'm not going to use this new way that we wrote the series. I'm going to stick with this original form. So we'll have 2x minus 1 to the n plus 1 over 4 times n plus 1 minus 1 over 2x minus 1 to the n divided by 4n minus 1. Alright, and then we'll use our absolute value signs. So this will simplify down to, well, let's see. Our 2x minus 1s will have a cancellation. We'll be left with 2x minus 1 on top, because n plus 1 minus n will leave us with just 1. And then we'll also need to multiply by 4n minus 1. And then we'll be left with, let's see, on the bottom that's 4 times n plus 1, so it's 4n plus 4 minus 1. So this is 4n plus 3. And of course, take an absolute value. So the important thing to notice here, and this time I'm not going to write out the math, but it's just that this part is going to go to 1. So by the ratio test, if we want this to converge, that means that the absolute value of 2x minus 1 needs to be less than 1. Right? We want this limit to be less than 1. We have that this part in red goes to 1. So all we're left with is the limit as n goes to infinity of 2x minus 1. And so that's why I'm saying that the absolute value of 2x minus 1 has to be less than 1. Well, this tells me that negative 1 is less than 2x minus 1, which is less than 1. So if I add 1 to both sides and then divide by 2, that will give me, well, let's see. I'm going to add 1 to negative 1. That'll give me 0, and then divide by 2. So I'll still have 0. Is less than x is less than. So I'll add 1 to 1. I'll get 2. And then divide by 2. That'll give me 1. And so if we think about this here, the distance from 0 to 1 is 1. If we cut that in half, that'll give us our radius of convergence. So r is going to be equal to 1/2. Okay. So now let's look at part 4, which is what is our interval of convergence? Well, we know that, we know that the interval of convergence is at least 0 to 1. And so what we need to do is we need to check x equals 0 and x equals 1 in our series for if they converge. If you plug in x equals 0, then you'll get that this converges, this series will converge by the alternating series test. Again, so I'm going to be leaving a lot of practice for y'all to practice these tests on these series. So go back and plug these numbers in and see if you can actually work out this test to get the same thing I'm getting. If you don't get the same thing, then please come to me and we can work on it. Now, if x is equal to 1, then the series will diverge by the comparison theorem. So that tells me that I is equal to, well, let's see, it converges at 0, so I'll include 0. But it doesn't converge at 1, so I won't include 1. Now let's look at example 3. For example 3, well, let's see. We have 2n factorial times 2x minus 5 to the n. Well, that's equal to 2n factorial. And let me make sure. Oh, I'm writing this wrong. We should have parentheses and then factorial sign. Okay, and then times. So I'm going to rewrite this 2x minus 5. I'll factor out a 2. So this is 2 times x minus 5 halves, all to the n. Well, then this is 2n factorial times 2 to the n times x minus 5 halves to the n. So then this part right here, this will be our c sub n. Similarly, this part right here is going to help us find the center of our series. And so we can see we'll have x minus a to the n has to be equal to x minus 5 halves to the n. So that tells me that a equals 5 halves is the center of our series. Alright. Again, so I'm doing this part in black, this part in maroon, this part in blue. So let's go ahead and try to find our radius of convergence. Just like in the past, typically when we see factorials and we can't cancel anything out, our first step should be ratio test. Okay, so I'll have the limit as n goes to infinity of, let's see. So plugging in n plus 1 for n, I'll get 2n plus 2 factorial times, let's see, so then we should have, again, remember I'm using this original form. I'm not going to use our new form where we got our c sub n. So then this will be 2x minus 5 to the n plus 1 divided by 2n factorial times 2x minus 5 to the n. Okay. So then this will be equal to the limit as n goes to infinity of, well, let's see, 2n plus 2 factorial divided by 2n factorial. That's going to leave me with, what will we have on top? We should have 2n plus 2 times 2n plus 1. And then 2x minus 5 to the n plus 1 divided by 2x minus 5 to the n will just leave us with a 2x minus 5 on top. And so we'll have nothing left on bottom. So I'm going to maybe write this a little bit nicer. Okay, and here's what I notice. This part right here is going to go to infinity. So the only way that we can stop it is if this part right here goes to 0. So that means I want the absolute value of 2x minus 5 to be equal to 0. Now, since we're setting this equal to 0, there's really no reason for us to have an absolute value because we're not changing the sign. Okay, so this means that 2x is equal to 5, which means that x has to be equal to 5 halves, right? And so this tells us that we only have one point, which is going to be x equals 5 halves, where this series converges. And so remember, when we just have one point where it converges, that means that r is going to be equal to 0. And then the next part is really nice because, well, we know that this is going to converge. We know it's just one point. So our interval of convergence is just written as 5 halves. Right? We use these curly braces to indicate that this is just one number instead of, a whole bunch of numbers. All right, now let's move on to example 4. So same general idea here. We start off by finding our c sub n. You should get that c sub n is going to be equal to, well, we already have our x minus a to the n up here. Right, I'm actually going to circle that in maroon because that's the color we'll be using for it. And so then our c sub n will be everything left over. So it's just going to be 1 over 2n plus 1 factorial. All right. Well, then the center of the series, so we should have x minus a to the n is equal to x plus 1 to the n. So a must be equal to -1. Right? Notice that if I plug in a equals -1 in here, then these two will be exactly the same. So a equals -1 is the center. Okay, now let's look at our ratio test. So for the ratio test, we'll have the limit as n goes to infinity of, let's see, so we should have x plus 1 to the n plus 1 over, plugging in n plus 1 for n, I'll have 2n plus 2 plus 1. So this is 2n plus 3 factorial divided by, well, now we'll just have x plus 1 to the n and 2n plus 1 factorial. As always, we take our absolute value. And so this will be equal to the limit as n goes to infinity of, let's see, so we'll have an x plus 1 on top. That'll need to be multiplied by 2n plus 1 factorial, which will cancel on the bottom with our 2n plus 3 factorial, so we'll be left with a 2n plus 3 times 2n plus 2 on bottom. And still keeping my absolute value signs in here. Okay, so what I notice here is that the bottom of this fraction is going to go to infinity. Notice that x plus 1, right, if we have something over infinity, the only way that this limit is not possibly converging, or, equaling something other than 0, is if our top is undefined. But x plus 1 is always defined, no matter what real number we choose for x. So you can think about this as a constant over infinity, which is going to be equal to 0. So this equals 0. No matter what x is. And so what this tells me is that our radius of convergence is going to be infinity, which means that my interval of convergence has to go from -infinity to infinity. Okay. Now let's take a look at number 5, which admittedly looks a lot more difficult. Okay, so we'll start off by finding our c sub n. Alright, so c sub n, we'll notice that we've already been given our x minus a to the n. We don't really have to mess with this. And so then c sub n will be everything else. So we'll have -1 to the n over 2 to the n times the natural log of n. Fun stuff, right? And so we can see right here that this c sub n is far more complicated than any c sub n we've been dealing with so far. Okay, well, let's next look at the center of our series. And so the center of our series is going to be, well, let's see, we'd have x minus a to the n equals x plus 1 to the n. So a equals -1 is the center. Before we continue, I want to give you an idea of why we're calling this the center and the picture that's being set up here. Let me go to this problem. I take it back. I do not want to do this one. I mean, we can do the picture here, you'll see, but it's not going to make as much sense. Let's look at something like this. Okay, what this means is that if I take some number line, right, here's our pretty number line, and here we're saying that the center of our series is, what did we say it was? Oh, a equals 1/2. Okay, so here's 0. Here's maybe 1. And here is the center. Oops. Here's the center, which is a equals 1/2. All right. And remember that this was 0 and this was 1. So the picture we can kind of get here is that if I use a different color, in this interval right here from 0 to 1, this thing converges. And everywhere else on the number line, this thing is going to diverge. Right? So the reason we call it the center of the series is because it's always right in the middle of our interval of convergence. Now, going back to the other problem, the reason I didn't want to draw the picture for this one is because our interval of convergence goes from negative infinity to infinity. So it seems weird to say that -1 is in the middle of negative infinity and infinity, right? You would want to say that 0 is in the middle. But that's not something we're going to get into. I just wanted to give you a picture of why we call it the center of the series. Okay. Another thing is that the center of a series, if you plug in that value for x, this thing is always going to converge because we'll be summing with zeros over and over again. Right, so notice if I take this series right here and I plugged in x equals -1, then I would get 0 on top. And our bottom would just be, positive real numbers. So we're just going to have 0 divided by positive numbers over and over again. So we're just going to be summing 0 over and over again. Okay. So now let's look at the radius of convergence of this thing. Well, noticing that I have this 2 to the n, it makes me think that we should do the ratio test here, which is exactly what I'll do. Now, when we do the ratio test, we're going to get the limit as n goes to infinity. We'll have -1 to the n plus 1 times x plus 1 to the n plus 1 over 2 to the n plus 1 times the natural log of n plus 1 divided by -1 to the n times x plus 1 to the n over 2 to the n times the natural log of n. So there's a couple things to be mindful of when we're doing the algebra here. One is that our ratio test calls for an absolute value. When we take this absolute value, -1 to the n plus 1 will always be 1. So it's not going to be affecting anything up here. So I'm going to get rid of it. Similarly, -1 to the n will always be 1. That's because we're taking an absolute value of this, right? So we know that when we plug in n for -1 to the n, this is always going to be 1 or -1. But once you take an absolute value of it, well, now it's always just +1. And multiplying by +1 isn't changing anything for us. So again, I'll get rid of this. Okay. Now I can rewrite this as the limit as n goes to infinity of, let's see, we should have x plus 1 on top. We'll multiply by 2n, but we'll have a 2n plus 1 on bottom, so I'll be left with a 2 on bottom times ln of n plus 1, and then we'll have times ln of n on top. All right, I need to point something out here. Ln of n divided by ln of n plus 1 is not equal to ln of n over n plus 1. Okay? We can't do that. Now, what I can notice is that as n goes to infinity, this right here is going to approach 1. Right? Because think about it. We'd have ln of 1/2, ln of 2/3. Well, actually, n starts at 2. So we'd have ln of 2/3, ln of 3/4, and so on, right? So this thing is going to approach 1. Now, let's look at another way you could look at that is think about, right, if we're taking the limit of just this part, if we do L'Hopital's rule on top and on bottom, then we're going to end up with the limit as n goes to infinity of n plus 1 over n. Right, and so we know there we can use highest degree rule, and that this thing is going to go to 1. Okay, now let's look at, we're going to be left with, oh, let me make sure I keep my absolute value signs in here. So we'll be left with the limit as n goes to infinity of the absolute value of x plus 1 over 2. Now we know by the ratio test that this thing will converge if our limit is less than 1. Right, so we want, let's see, this 1/2 isn't going to be affected by the absolute value, so I can call this 1/2 times the absolute value of x plus 1. I want this to be less than 1. Well, multiplying by 2 on both sides, I really just want this absolute value of x plus 1, to be less than 2. Okay, so this is saying that I want -2 to be less than x plus 1, which should be less than 2. Now I'll subtract 1 everywhere, so I'll get -3 is less than x is less than 1. And so remember we said that a equals -1 is the center, and that's going to be right in the middle of this interval here. Okay, so then we know that the interval of convergence, let me go ahead and write down the radius of convergence. This thing has a length of 4, and so we can say that the radius of convergence is going to be equal to 2. Alright, so then our interval of convergence is at least -3 to 1. And so what we would need to do is test our endpoints. Well, x equals 1 is going to converge by the alternating series test, and x equals -3 will diverge by the comparison theorem, which will, in that you should use the p-series. So I will be equal to -3 to 1, including 1. Okay, now let's look at some different styled problems. Here on example 6, we're given some power series, and we're told that it converges at x equals -4, and it diverges at x equals -6. So the first thing I want to do here is notice that the center is a equals 0, right? Even with what they've given us here, I don't know exactly what c sub n is, but I know that x minus a to the n has to be equal to x to the n. So then the center must be x equals 0. Okay. And I know that it converges at x equals -4, which tells me that, so the distance from 0 to -4 is 4. So r is at least 4, right? I know that r isn't going to be equal to 3, because if r was equal to 3, then our interval of convergence wouldn't include -4 right here, right? But we're told it converges there. So what I can say here is that everything from -4 up until +4 must converge. Now, since I know that it diverges at x equals -6, I can say, but it has to be, it can't be bigger than 6. Right? So here, what we can tell is that the interval of convergence is at least -4 up until 4. We're not told that it converges at +4, right? Remember in the past, whenever we said something was like, let's see, where did we say it? Right? Here we said r equals 2. And so we didn't include these points. We had to test for the endpoints. So I'm basically doing the same thing here. I'm starting off with how we would normally do this, but then I changed this to a bracket because we're told that it converges at x equals -4. Okay. So now if I draw a picture, so let's see. We'll do something like this. Here we have 0, which is going to be our center. Okay. And we know that, let's see, from -4 to 4, we know for a fact that this area right here, right, so everything in here converges. Now, we also know that at -6, this thing diverges. So let's see. I'll use a different color here. So this is -6. So everything from -6 to -infinity must diverge. Similarly, everything from +6 to infinity must diverge. Now what we don't know is this area in here. So from 4 to 6, we don't know what's happening in here. And from -6 to 4, we don't know what's happening in here. So let's look at each of these series. So for part A, we're given that the x value right here is equal to 2. So we're given x equals 2. So then A is going to live right here. And so we can see that that's inside the part that we know converges. So we know that this converges. Now let's look at part B. For part B, we're given that x is equal to 8. Sorry, I didn't mark this down. So this is B right here. And this is then the area that we know diverges. Oh, sorry. We had x equals 8. Diverges. Okay. Now part C, we're given that x is equal to 4. And so that's actually going to be right here. We'll notice that the plum color does not include 4. However, this maroon color right here does include 4. So that means that C is sitting in the area that we don't know anything about. Right, so this was at x equals 4. And so what we say is that there's no conclusion. Right, so we write NC. Now, for the next part, we will have part D. Let's see, we can put it right here. For part D, we're given that x is equal to -5. And so notice that x equals -5 sits in here. Right, so this is part D. And so that's going to lie in this maroon area. And so again, we say that there's no conclusion. So the goal on these types of problems is to draw out this number line and figure out what areas do you know it converges in, what areas do you know it diverges in, and what areas do you have no idea about. Okay, we do that by figuring out what R can and can't be, which will help us figure out what I is going to be. Now let's look at example 7. So this one's a little bit different, mainly because of the fact that our center is no longer 0. So notice that our center right here is A equals 1. Alright, so I'm going to start by drawing a number line. Alright, so this will be 0. This will be the center of our series, which is A equals 1. Alright, we are told that this interval certainly converges when x equals 3. So let's say 3 is right here. So I know that in this area, we converge, which tells me that R has to be at least 2, right? So what I'm going to do is I'm going to go 2 tick marks, or 2 units left of 1. So then I know that from -1 to 1, this thing will also converge. Right? When I'm told that this series converges when x equals 3, then I figured out that R is at least 2 by doing 3 minus 1. Right? Figuring out what is the distance from this point where it converges to the center of our series. Once I got that R was at least 2, then I knew that I, remember from our rules, I is at least -r plus a to r plus a. Right, and so this is -2 plus 1, right, because that was our a value, to 2 plus 1. There should not be a comma there. Right, so this is from -1 to 3. However, in the problem, they tell us that it converges at 3, so I know that this has to be a bracket. And so this is going to be the largest interval where we can guarantee that our power series must converge. Okay, so that'll be the end of power series. If you have any questions, please feel free to bring them to me. And also, please make sure that when I'm writing things in here, right, so things to practice are going to be applying the tests here, right? So plug in x equals 1 into the series, and then right now the only thing you're going to have is constants and n, so you can use some sort of test. Here I'm telling you to use the alternating series test to get that this thing converges. Right, so let me go ahead and circle the parts that I would like you to practice. So again, this part right here is a good part to practice. Here's another good part to practice. And then that should be it. Alrighty, thank you very much.